Integrating Kafka with Elasticsearch. Take it away.
Okay, thanks everyone. So in this talk, I'll focus more on microservices patterns with Kafka. So I'll take a couple of use cases and a couple of patterns related to microservices and elaborate on how you can leverage them with Kafka and other ecosystem components. Brief introduction about myself. I'm actually from a company called WSO2, which is an open source middleware provider. We work on API management, integration, and IAM domain. I work mostly on integration and microservices related stuff, and also recently wrote a book on microservices. Also, I run a meetup on microservices in Bay Area. So to give an overview of the session, I'll talk about the importance of integrating microservices, the need for integrating multiple microservices and create compositions, and some of the patterns that are involved in creating integrated microservices, such as active or synchronous composition or orchestration or choreography or reactive composition. And then I'll go into the details of how these patterns can be implemented with the Kafka ecosystem. All right, so as you know, with the rise of cloud-native applications, what we are seeing is the disaggregation of multiple services and serverless functions, right? So we used to develop a software application as a single monolithic runtime, and now we segregate that into independent, networkly dispersed services or functions. So that means you need to create this kind of business capability oriented services, but when you have to build some business use case, you need to have some kind of a coordination or some kind of a composition of these microservices or serverless functions. So that is the problem of integrating microservices or creating compositions out of your existing microservices. So if you have a look at some of the concept around integrating microservices, we can identify three different main concepts. So first one is, of course, the APIs, right? So you create a service, you probably expose maybe a RESTful interface to your service. An API can have two parts. You can have command portion, which can change the underlying entity, as well as query part, which is basically a request for information. And also the other aspect of integrating services is events. So you are receiving events to your service, or your service provides or produces events to other services. The extended version of event is streams, right? You have, rather processing a single event, you process a sequence of event over time. So if you look at the synchronous or API-driven approach, when it comes to integrating or creating compositions using synchronous style, we have in this particular architecture, you can see there are multiple levels of microservices. So probably at the bottom, you can identify microservices which are core or atomic microservices, which are not really talking to multiple other services, right? Maybe you can consider them as fully self-contained, which don't have any network interactions. And then you can have composite services, the services that talks to some other microservices, right? And by creating composite services, you may build some business capabilities or composite business capabilities. And of course, if you are using microservices in practice, you may be exposing most of your microservices to your consumers. So often that is done through an API gateway layer. So in this architecture, we have API management, which is the functionalities that you are exposing to your consumers, to your customers or partners, exposed from the API layer, but all these services are centrally managed by an API management layer. So that is the place where you apply versioning, security, throttling, caching. So likewise, entire API ecosystem is built at that layer. And it's important to understand that this is not a monolithic layer. It is not a single monolithic runtime running as an API gateway. but this is more or less micro gateways. A given API runs on its own gateway kind of thing. Okay, so, and also, of course, you will have your on-premise or existing or proprietary systems which are already there in the organization, and you can create wrappers around those systems using other services. So this is the active composition architecture. In this architecture, you have service-to-service direct communication. And if we move into the possible implementation technologies, we have obviously RESTful services is the most commonly used technique. gRPC is getting very popular, especially when it comes to building internal compositions. Internal service-to-service communication usually implemented using gRPC. GraphQL is also popular, especially when you have services which are not really resource-oriented, which services that you need to change the output based on the client's request, client's behaviors. So GraphQL is getting very popular in that domain. WebSocket Thrift, not that popular, but two possible techniques. So let's move on to reactive composition or choreography. So as you know, as you may have heard, microservices, we foster the elimination of dependencies, right? You need to create services as autonomous units. So having asynchronous event-driven communication is one of the fundamentals to make your services autonomous. So unlike synchronous composition, here you have a set of services, and we use a central event bus, right? And from a given service, you can produce messages to maybe a topic or a queue, and there can be a consumer who is subscribed to the same topic or consuming from the same queue. So there is no direct service-to-service communication, but intermediate event bus is handling all the communication. And one other aspect of this architecture is that the central event bus shouldn't have any business logic. It must be a dump message broker. So that's why brokers such as Kafka is getting very popular, because unlike if you have heard of things such as MQ series products like TIBCO MQ and or the other enterprise-related brokers, they have a lot of business logic within the broker. But Kafka, the logic resides between the producer and the consumer, and you have a lot of control at producer and consumer level. So implementation technologies, we have Kafka, MQP, and JMS. So these are the most commonly used techniques for asynchronous event-driven communication. So let's move into Kafka as an implementation technology for this kind of reactive compositions. I think most of you are familiar with Kafka architecture, so I'm not going into the details, but at very high level, Kafka is a distributed event log. And when it comes to microservices, Kafka provides the central event bus foundation so that producers can produce message to the Kafka broker and the consumers can consume from the broker. So the producers can produce to a given topic, and topic can have multiple partitions, and if need, producers can decide to which partition that it wants to publish using the key. And at the consumer side, you can have one topic can have multiple consumers and different consumer groups. So likewise, all the Kafka-related concepts are applicable in most of the microservices patterns. So let's look at some of these patterns. So the first one is, of course, the publisher-subscriber. You have one producer or multiple producers producing the messages to a topic. And then you can have multiple consumers from different consumer groups, and they can consume messages from the Kafka broker. So this is a very standard, straightforward messaging pattern. And consumers of a given consumer group can only consume from one partition, right? We don't really allow partition to be shared between members of a given consumer group. So the other pattern is single consumer. So this is often used for in-order delivery or queuing. So in this case, we have a single consumer who's publishing to a given topic, and the consumer is basically poll the topic and sequentially process using the offsets. So both are like very similar patterns and straightforward patterns. Now, things get a little complicated when we have things such as exactly once delivery semantics. So earlier it was also discussed. But so exactly once has different definitions, but in this case what we are actually talking about is you can publish messages from a given producer, and it ensures that the message is delivered one time, exactly one time to the receiving application. So receiving application will receive the message exactly once, right? So this is a very common requirement, right? If you are doing any kind of transactions, this is a very common requirement. So when it comes to implementing this kind of patterns using Kafka, there are two areas that we have to aware of, right? So the first one is the producer. So when producer starts writing the messages to the log, and before it gets the acknowledgement, it fails, right? So that's a failure at the producer side. And also at the consumer side, once the consumer reads the message from the Kafka topic, but it fails to update its offset, right? In that case also, message is already read, but its offset is not updated. Maybe when after a crash happens, when during the next restart, it will read the same message because offset is outdated. So how do we avoid these two failures? So Kafka by default provides something called idempotency producers, so that you can produce messages to a Kafka topic any number of times. So that Kafka will, and you will have duplicates, of course, but Kafka will take care of all the duplicates. So that means when you are implementing the exactly once delivery pattern, you can use this kind of idempotency producers so that it can retry as many times you want. So to avoid consumer side failures, so offset is the key, right? Handling the offset and handling the content of the message is the key. So therefore, at the consumer side, you may be using a database to process the message. And at that point, you may use the same offset in the same database and store them in the same transaction, right? So let's suppose that you read some content of an order, like a retail system, you read the content of an order, and once you store the order in your database, you also store the offset along with in the same database in the same transaction. So same transaction boundary covers both offset and the content of the message. So with that, you can ensure the consumer side delivery as well. So there's a link below. There are details on this pattern explained in a Medium post. All right, so the next pattern is event sourcing. I think most of you may have heard of event sourcing. The main concept behind event sourcing is there is a producer application. The producer application persists each and every state-changing event in a distributed event log, and these events are immutable. And different subscriber application can consume those events and recreate the state of that application at the consumer side, right? So for example, in this example, you have different states of orders recorded in a distributed event log, and the consumer applications can basically process the event log and materialize it based on these applications' requirements. So Kafka becomes a really good candidate for implementing this kind of pattern, again, due to the nature of dumb broker behavior, as well as the scalability and being a distributed event log, so that you can record all these immutable events. So now we talk about APIs, events, and streams. So when it comes to streams, you can write microservices that process event streams, right? So in this case, either you process an event stream as an inbound set of data, or you produce events to a particular stream. So in a microservice that process events, basically what you have is the business logic that continuously process set of incoming events. And Kafka streams is becoming one of the popular libraries to process a stream of events. So basically you write your microservice and start consuming inbound set of events, and maybe you produce an output, maybe call another service, or maybe create another event stream out of the incoming event stream. So there is an example from Kafka streams, which is like a very straightforward word count example. So CQRS, this is an application of some of the things that we have discussed earlier. So there are services that you need to have some kind of a separation between your command and query part, right? The requests that are changing your underlying entity versus requests that are only getting data, only doing the query part. So usually this can be implemented by using two different databases and two different services. So you build your query service backed by a given database, and then you build your command service, again backed by its own database, and there is a synchronization happen between these two databases. But with Kafka, this is actually relatively straightforward to implement. You don't really have to use two different databases. Rather, you implement the command side using the conventional Kafka topic. Basically, the command side application writes data into Kafka topic. And on top of that, you'll build a Kafka event stream, which basically materialize the content of the Kafka store and build a query stream out of that. So basically, this side can be a stream-backed REST service, for example, right? So here we have something called interactive queries in Kafka stream, where you build a query kind of an interface on top of the Kafka data store and expose a RESTful interface on top of that. So when you are using Kafka, using schemas is also very important, right? And because when you have multiple microservices, one microservice produces events to the underlying event store, and there are other consuming microservices. So you need to have some kind of a consistency between data that are flowing between all these services. And as you know, by default, Kafka does not look at your data, right? You can do anything. You can pass any byte stream or anything. But having this kind of schema across these collaborated microservices is important. So Avro is possibly the de facto standard that you can use along with Kafka-backed microservices architectures. So when you are using Avro, there are a few things that we need to consider. So what you basically do is you associate a given Avro schema with a topic. And Avro, so having that kind of a schema and using Kafka schema registry allows you to declare the requirement for the data that is produced into the topic. So when you're producing the data, it will ensure that all the required data is there, or it will fail the event publishing job. And when you're consuming also, you can, by using the schema, because both are sharing the same schema, producer and consumer, so therefore you can provide whatever the instructions on how to serialize data and how to read data from the consumer side. So try using Avro as the schema when you are having a collaboration between microservices with Kafka. So Kafka Connect, so usually when you are having this kind of Kafka-based systems, it is very unlikely that you will have only Kafka as the system, right? You will have a lot of your on-premise data. You will have databases. You will have file systems. So Kafka is sort of provides you the capability to integrate with existing Kafka Connect provides you the capability of integrating with existing databases or file systems. You can use source databases, source systems, as well as sync systems. So here you get data from all these different data sources and pump them into Kafka, as well as you can create syncs out of the existing Kafka topics, for example. So if you look at the entire Kafka ecosystem, what you have is Kafka is used as a single source of truth, and you have streams on top of it. You have connect and other connecting components on top of it. And one important thing is Kafka Connect is, we cannot really consider that as an integration framework kind of thing, right? It will allow you to integrate with some of the existing databases and file system, but it is not something like, I would say, Camel or Mule or WSO or any kind of integration platform. So if you are having some kind of integration requirements, still you need to cater, and still you need to have integration between Kafka and those systems. So now we talked about synchronous composition and the reactive compositions. Let's have a look at pros and cons of both of these approaches. So of course, active or synchronous composition is ideal for interactive services, services that accept a request and immediately respond with something. So that is very important to have that kind of synchronous communication. And of course, we can build request response model on top of asynchronous, like a event-driven architecture, but it will be very complicated for a simple request response service. So obviously, orchestration or active composition makes your services dependent on other services, right? When you have a composite service that calls multiple other services, that means your service is dependent on all the underlying or the downstream services. With reactive composition, it's ideal for asynchronous interactions like order processing, shipments. Reactive composition is ideal, but the problem is composition logic is opaque. So by looking at a single service, you cannot really see what's going on. You need to look at the entire set of service. So probably the best way to identify or deduce the ongoing composition is to have proper observability across all your services. So the producers maybe use something like Elasticsearch. Producers publish events, consumers publish monitoring events, so that you can have a central observability view of all the ongoing transactions. And so what we can propose is something like this, which is a hybrid of synchronous communication. Your APIs are more or less doing synchronous communication, and internally you use Event Bus and Kafka for all the synchronous messaging. And when it comes to building this kind of hybrid compositions, it is important to bridge your request response model and your asynchronous event-driven model, right? In this particular diagram, you can see there are like multiple event-driven microservices along with the REST interface, right? RESTful service. So what we can actually do is we can create a so you can have Kafka as a synchronous event-driven event log, and you can create a queryable materialized view out of the existing Kafka topics using Kafka streams. So it will look like something like this. So you will create a Kafka stream, and then you materialize the existing data. And once you materialize it, you will get an event store, and you can implement your as shown in the bottom, you can implement your RESTful interface on top of the materialized event store. So this pattern is also commonly used if you are having like an entire Kafka ecosystem. This is a commonly used pattern. So some of the implementation technologies that you can realize these patterns, of course, Java is probably the most powerful one when it comes to all the different components that I talked about. And you can have a look at this Confluent microservices example, which is like a fully fledged microservices example on how to implement all these things with Confluent platform. Of course, Go, Python, .NET offers a rich set of capabilities. Again, Kafka is language independent, right? You can use any language and still you can use that as a broker. And also, as part of WSO, we have been working on a language called Ballerina. So because we have been working on the integration space for a long time, and we try to come up with a dedicated language that allows you to create this kind of microservices composition. So you can have a look at ballerina.io, and it has like a native network-driven concept built into a language. For example, things such as service, resources, endpoints, circuit breaker, all those things are part of the language. And you have multiple connectors like HTTP, Kafka, gRPC. So you can take a look at the language. And also when it comes to integration frameworks, you can use Apache Camel, Spring Boot, and all the other frameworks, basically to create compositions and using Kafka as the event broker. All right, so that's all I had. So if you have any questions, we can take a couple of them.
Any questions for Kasun? Over here.
So what do you recommend if you have like huge messages, like around 4 or 5 MB worth of messages going into Kafka? What are good practices to do? Should we send, like, compress those messages onto Kafka? Should we store them somewhere before sending? What do you suggest as a practice?
Yeah, so so it depends on the content. So if you take like a 4 MB message, and if you have to process the entire content of the message, of course, you need some kind of a streaming capability, right? So what I'm talking about is you get like a 4 MB message and you transform it to another 4 MB message, maybe with XML to JSON kind of thing. So then in that case, I would say you need some kind of a streaming capability. And for files such as like video files or some other like very large files, probably you can use the event bus as the reference, like a link. You'll have a link to the reference to the actual content of the file, and you just do the routing based on the metadata. So I would say, based on the requirement, you can select either of those approaches. Yeah. Yeah.
Can you elaborate more on the GraphQL composition?
Yeah. Yeah. So in GraphQL, so in normal RESTful services, you have set of resources, right? Suppose that you have orders, customers. So when you want to retrieve data of a given order, for example, the client might not need all the data, right? Or client might only need the order's description and the amount, maybe. So when you send a GraphQL query to the service, as part of the request, you can specify, I need order ID, order description, and order amount. That's all I need. So when you receive that to the GraphQL-driven service, it will only send those data. And same client can include order date or something. Along with the request, it can ask for the order date. And by looking at the thing, the service can send the order date along with the response. But in the normal RESTful world, it's really hard to do that, because if you need all the data, then it's all or nothing kind of thing, right? You have to send all the data or a portion of it. There is no intermediate thing that you can control. So that's why GraphQL is getting popular, but it's slightly against the normal resource-oriented or RESTful services concept. It works for both GET and POST as well. Yeah, because as part of the POST request, you can send some ID or something. I need order ID this one, and then you can retrieve that order. So it's a POST, but still sort of a GET.
All right. Thank you so much for that talk, Kasun.
Thank you.
Great presentation, and let's have another hand for our other presenters, Suyog and Ying and Dan from our own left. Thank you so much, everybody, for coming in and sticking it out through the whole evening. And we hope you enjoyed your visit here. You got some pizza, take home some swag. Elasticsearch Meetup Groups holds these meetups semi-frequently at different venues all around the city. I highly encourage you to go visit them wherever they may be popping up. Usually Matt or somebody else is there organizing things. And I hope everybody has a great night. Thank you.